In this video, we'll examine the multi-degree of freedom system shown in the figure, and in particular, we'll find the equations of motion using Lagrange's equations, and from that, the mass and stiffness matrices for the system. The system comprises a pulley of mass big M, and it has a mass moment of inertia J sub 0, meaning J about its center, which is labeled 0 or O. The pulley is attached to a rigid surface by a spring of stiffness K, and then hanging from the pulley are two masses. On the right-hand side, we have this mass 3m, and that is hanging on the edge of the pulley, which is a distance of 3r from the center. On the left-hand side, we have a mass of little m that is attached to the pulley by a spring of stiffness 2k, and it is attached a distance of r from the center of the pulley. In addition, this mass m, little m, is attached to another rigid surface using a spring of stiffness 3k. We are given coordinates to use in this problem. x1 is the motion up and down of this pulley. That is x1, as I've drawn in the diagram. x3 is the motion of this mass, little m. And x2 is the motion of the big mass, 3m. This is x2 here. So it should be noted that 3m displaces as a result of x1, and also as a result of the pulley displacing by an amount theta. That causes this mass to displace. Those two displacements added, combined, give you x2. In addition, we have forces F1, F2, and F3 respectively acting on the 3 degrees of freedom, x1, x2, and x3. So the first thing we should note is that there's a relationship between x2 and x1, and that relationship has to do with the angle of rotation theta of the pulley. Specifically, we can say that x2 minus x1 is equal to 3r times theta. Therefore, theta can be written as x2 minus x1 divided by 3r. And taking time derivatives, we find that theta dot, the velocity of theta, is equal to x2 dot minus x1 dot divided by 3r. Okay, and I'll copy that result to the next page. So moving on, I have copied the results of the previous page here on the left regarding theta and theta dot in terms of x1 and x2. And in order to solve using Lagrange's equations, the first order of business is to find expressions for the potential and kinetic energy of the system. I'll start with the potential energy, which we call V. And V is equal to, well, let's start off with each of the springs. So the first spring, the spring at the top, would give an energy of 1/2 times k times the deflection of that spring squared, which is x1 squared, plus, looking at the spring at the bottom, 1/2 times 3k times the deflection of that spring squared, which is just x3 squared, plus the other spring, which is 1/2 times 2k, times the deflection of that spring squared. Well, the deflection of that spring squared is simply x3 minus x1 minus r theta. Let me write that out. x1 minus r theta, and that quantity is squared. Why x1 minus r theta? Because x1 causes the spring to move in that direction. R theta causes the spring to move in the opposite direction, and that's why we have the negative sign. And by subtracting the two, we get the actual deflection of the spring. So that can be rewritten as 1/2 k x1 squared plus 3 over 2k times x3 squared plus the 2's cancel, k times x3 minus x1 minus r or plus r theta, I should say. But r theta from here is just x2 minus x1 divided by 3. So this is plus x2 minus x1 divided by 3 quantity squared. And I'm not going to bother simplifying it. In general, I find when using Lagrange's equations, you're going to take the derivative anyway. So rather than multiply this all out, we'll just leave it in this form. We'll call that equation 1. Okay, and then the next thing to do is find an expression for the kinetic energy, which we'll call T. Kinetic energy T is a half times mass times velocity of each of the masses. So let's start off with this little mass at the bottom, is 1/2 times m times the velocity of that mass squared, which is just x3 dot squared, plus, let's take the pulley. Wait, I'm making a mess. Let's take the pulley. It's plus 1/2 times big M. And the velocity of that pulley is x1 dot squared plus the mass 3m. So it's 1/2 times the mass 3m. Oh, let me write it this way. Let's just say 3/2 m. And that is coordinate x2 dot, the velocity of that, x2 dot squared. And now, since this pulley has rotatory inertia, we need to include that effect as well. And that would just be plus 1/2 J0 times theta dot squared. But we have an expression for theta dot, which we can substitute in there. So rewriting it, it's equal to 1/2 mx3 dot squared plus 1/2 big M x1 dot squared plus 3/2 little m x2 dot squared plus 1/2 J0 times x, let's see how I want to write this. It's times x2 dot minus x1 dot divided by 3r. So let me just write that out. x2 dot minus x1 dot divided by 3r quantity squared. And I'm actually just going to square this and take it out. So I'm going to choose to rewrite this just because I think it's a little bit more compact as 1 over 18r squared. So it's 3r quantity squared gives me 9r squared times 2 is 18r squared times J0, J0, times x2 dot minus x1 dot quantity squared. And that is the expression for the kinetic energy. So the next step is to substitute these into Lagrange's equations. Let me write out Lagrange's equations here for reference. All right, and since t is just a function of the velocities and v is just a function of the displacement, I can write Lagrange's equations in this form. Time derivative of partial t partial q dot I plus partial v partial q I is equal to the generalized force, capital Q sub I, where I is equal to 1, 2, 3. Okay, I just put it in green so I could keep it separate. Let me change back to black. So now we need to take the derivative with respect to each one of the generalized coordinates. So starting off with x1, the derivative of the kinetic energy with respect to x1 dot gives me, there's an x1 dot there and there's an x1 dot there. So those two terms. So the first one gives me big M x1 dot, and take the time derivative of that gives me a double dot. Okay, minus j0. The derivative of this is, using the chain rule, is 2 times x2 dot minus x1 dot times the derivative of x1 dot, which is minus 1. So I get a minus sign, j0 over 9r squared, because I multiply by 2, times x2 minus x1, and those take a time derivative of those, which give me a double dot on each of them. Maybe take a second to convince yourself that's correct. Plus, and now take the derivative of v with respect to x1. So these two terms have x1 in them, actually those three terms. And that gives me kx1 from the first term, plus 2k times, the 2k comes from taking the derivative of this, 2 times k times the derivative of what's on the inside. And the derivative of what's in the inside is, it's 2k times this, times x3 minus x1 plus x2 minus x1 over 3, times the derivative of the inside. The derivative of this gives me minus 1. The derivative of this gives me minus a third. Minus 1 minus a third is minus 4/3. Okay, and what I'm going to do, just to save space, is I'm actually going to multiply the 4/3 by 2, which gives me minus 8/3. Just to make it a little bit compact. So this would be minus 8/3. Okay, and that is equal to the generalized force, which in this case is F1. Simplifying this, I can write it as m plus j0 over 9r squared. So let me group that. M plus j0 over 9r squared times x1 double dot minus j0 over 9r squared times x2 double dot. And now let me collect the x1 coefficients, and that gives me 1 plus 8/3 minus, or plus 8/9. So that would give me 1 plus 8/3 plus 8/9. That is 41 over 9. Kx1 minus kx2 is minus 8 over 3 times 1/3 is minus 8 over 9 kx2, I should say, not 3. And then minus kx3 is minus 8 over 3, just minus 8 over 3. Kx3 is equal to F1. And that is your first equation of motion. We'll number that number 3. All right, I'm going to start a little bit more to the left here just to make some room for myself. For the x2 equation of motion, we proceed exactly the same way, except now we take the derivative of t with respect to x2 dot. We find when we do that, we get where are the x2 dots? So it's this term here and this term here. So the first one gives us 3/2 times 2 is 3 times m times x2 double dot, because it's the time derivative of that, plus from here we get j0 over 18r squared times 2, so it's j0 over 9r squared, times what's in the parentheses, which is x2, x2 minus x1, and the time derivative of that, which gives us a second dot on top of them. So that's a double dot. Plus, and now we're going to look at v. We want to take the derivative of v with respect to x2. Well, it's only this term here that contains x2. So it's 2 times k times what's in the brackets times the derivative of what's in the brackets. So 2k times what's in the brackets is x3 minus x1 plus x2 minus x1 over 3 times the derivative of what's in the brackets with respect to x2. What's in the brackets is just a third. So in fact, I'm just going to write this as 2/3. Okay, and that is equal to the generalized force on that coordinate, which is F2 in this case. Let's simplify it, starting off with x1 double dots. We got negative j0 over 9r squared, so negative j0 over 9r squared x1 double dot. We can group the x2s, so this is plus 3m plus j0 over 9r squared times x2 double dot minus, let's look at the x1's terms. You've got minus 2/3 minus 1/9. Sorry, minus 2/3 minus 2/9 is minus 8/9. K times x1. Times x2, you've got just 2 times 2 over 9, so it's plus 2 over 9 k x2. And then x3, it's just 2/3, so plus 2/3 k x3, and that is equal to F2, and that is equal to equation 4. We'll number that. Okay, so the only thing left is to do the last equation for coordinate x3, and that is, let's do it down here, x3 if I take the derivative of the kinetic energy with respect to x3, it's only that term there, so that's easy. That's just m x3 time derivative gives me a double dot minus the potential energy with regards to x3 comes out in both those terms. So the first one is just 3/2 times a half is 3, so it will give me 3kx3. 3kx3 plus, taking the derivative with the chain rule, 2 times k times what's in the brackets, x2 minus x1 plus x2 minus, oh, I made a mistake here. Should be x3 minus x1. It's just what's in the brackets here. So x3 minus x1 plus x2 minus x1 divided by 3 times the derivative of what's in the brackets with respect to x3, and that is just 1. That makes it easy, and that is equal to f3. Okay, simplifying this gives me mx3 double dot minus x1 is 2 minus 2x1 minus a third x1 is minus 8 over 3. So minus 8 over 3 k x1. For x2 I get 2 over 3 plus 2 over 3 k x2. And for x3, I've got minus 3, and oh, I made a mistake. That's not a minus 3, that's a plus 3. Excuse me, my bad. So plus 3 plus 2 is plus 5. K x3 is equal to f3, and that's equation 5. So equations 3, 4, and 5 are your equations of motion, and all that's left is to write it in matrix form. I'll do that on the next page. Okay. So what I've done here is I've just copied the equations of motion from the previous page. And now in order to write this in matrix form, we can write it as m plus j0 over 9r squared. This is minus j0 over 9r squared. And this would be a 0. The next equation, this would be minus j0 over 9r squared. This would be 3m plus j0 over 9r squared. And this would be 0. And then 0, 0, little m. Times x1 of t. x2 of t. I'm putting the t's back in here. I just omitted it to keep it concise. Plus, oops, plus, this would be 41 over 9. Okay, minus 8 over 9, k, minus 8 over 3, k, minus 8 over 9, k, 2 over 9, k, and 2 over 3, k. And then minus 8 over 9k, minus 8 over 3k, I should say. Two-thirds k, and 5k. Whoops, that's not a very good bracket. This is times, oh, I made a mistake. This should be the acceleration. I left off the double dots here. Please don't do that. x1 of t, x2 of t, x3 of t, and that is equal to the vector of generalized forces. In this case, it's f1 of t, f2 of t, and f3 of t. And in doing so, I've now written this in the form of m times x double dot of t plus k times x of t is equal to f of t, where obviously this is the M matrix and this is the K matrix. And that's it. We're done. Thank you for watching this video. I hope you found something useful in it. If you did, please go ahead and leave a comment below, or better still, subscribe to the channel. Thank you for watching, and we'll catch up with you in the next video.